My name is Kate Eltham, and I'm the chair of this session, Nanotechnology from Sci-Fi to Reality. But I should make a confession from the beginning that I am not a scientist, and I know very little about nanotechnology, so I'm going to be asking all of the dumb questions that I hope our panel will be able to shed some light on during this session. I first learned about nanotechnology about 15 years ago when I read a short story by the science fiction author Greg Bear called Blood Music, which was a fascinating dystopian horror story about what might happen when nanotechnology goes wrong or gets out of the box, so to speak. And I'm sure that our panel is going to tell us about some of the far more optimistic and practical applications of nanotechnology than what I found out about in that story. So let me introduce you to our panel, and then I'm going to ask them to just speak briefly about the work that they're doing and what they see as some of the applications and potential for nanotechnology. And then we'll have a bit of a discussion around those topics. On my left, we have Dr. Nina Mitter, who is the Principal Biotechnologist at Primary Industries in Queensland. Then we have the three Peters at this session. We have Dr. Peter Talbot, who is the Chief Scientist of the Very Small Particle Company. Next to him, Dr. Peter Camburas, who is the Director of Innovation and Commercial Development for the Exploration and Mining Division of CSIRO. And we have on the end Professor Peter Gray, the Director of the Australian Institute of Bioengineering and Nanotechnology. Would you please welcome all of our presenters this morning? I'm going to go to the end of the panel and ask Professor Peter Gray if he might kick us off and just give us a little bit of an introduction about the work that he's been doing in nanotechnology.
Well, thank you, Kate. And as the introduction said, I'm Director of an Institute of Bioengineering and Nanotechnology at the University of Queensland. It was built with funding from the State Government of Queensland, an American philanthropist, Atlantic Philanthropies, and the University of Queensland. We have 18 research groups, 360 people total, over 100 PhD students working on a range of areas. But I thought I'd just mention two examples, one in the energy and the environment area and the second in the healthcare area. The first in the energy environment area is work we're doing on moving towards a hydrogen economy. We use hydrogen cars. We're all very attached to our automobiles. We all realise that crude oil is finite. So it would be easiest if you could just take your car along somewhere and fill it up. Now, why hydrogen? Well, hydrogen is perfect because when you burn hydrogen in a fuel cell, you get water vapour. No CO2, no nitrous oxides, no contaminants. So it's a very nice concept, but there are a few technical problems in the way. One, where to get the hydrogen. Two, how do you store it in the automobile? Now, in AIBN, we have groups that are working on both those areas. One, on using nanoparticles to absorb the hydrogen, so you can have a small cube in the boot of the car that's absorbing enough hydrogen to last you several hundred kilometres. And the second is, how do you get it? And we have groups working on photovoltaic cells using nanotechnology. You can take sunlight, hydrolyse water to generate the hydrogen. So in a sense, those technologies we feel are going to be the future when you get to totally renewable hydrogen economy. Now, Peter will talk a bit about some of his exciting work on electricity storage, which in a way links into some of those areas. The second and final example is the work we're doing on stem cells. Now, stem cells are what's called pluripotent cells, meaning they can make any cell type in the body. So if you're trying to get cells to replace damaged heart tissue, cells to replace damaged nerve tissue, you can start with a stem cell, grow it and direct it towards a particular cell type. Now, in the body, our stem cells sit in very specialised areas like the bone marrow, where people talk about the stem cell niche, where there's a nice little pocket that the cell can sit in and it gets all the right signals, all the right sorts of proteins, all the right indicators saying, I want to keep growing as a stem cell. Now, what we do in nanotechnology is to try to reproduce that patterning at the nanometer scale. So the cell that's about 20 microns long, which is 20,000 nanometers, might have hundreds of different proteins it can see, sit on, and say, this is telling me to be another stem cell. Then eventually you move it to somewhere that says, this is telling me to become heart tissue cell. 2 examples. We have many other programs going on, but in my 5 minutes, I think that's it, Kate.
Thank you, Peter.
So from an exploration and mining perspective, what we're interested in doing is we don't actually make anything that's nanotechnology related. What we do is we utilise tools that are nanotechnology related. Just have a couple of demonstrations here. Everyone's seen standard light on your bike. One bulb, 90% of that energy is heat. Think about that in an underground coal mine with lots of methane. Okay? Was this being used in 1970? Yes. Was this being used in 1980? Yes. 1990? Yes. 2000? Yes. 2005? Yes. Today, they're still using this. They haven't discovered this. This hasn't been adapted into an underground coal mining environment. These are light-emitting diodes. Light-emitting diodes are only made possible by ability to change materials. And that's what nanotechnology is about. The intensity, the energy consumption, and also the safety factor. Nearly 80% of the energy is light here. There's not a lot of heat coming out. So what we do is we look around for how we can utilise new technologies, firstly to improve safety, and then to improve productivity. Another question for you. In an underground coal mine, I've never been there myself. Anyone in the audience been in an underground coal mine? Okay, so you've got 200 metres of black. Underground, it's pitch black. How do you know where you're walking? How do you know where you're driving? How do you know when you're cutting a new wall? String line. String line was utilised, well, it's still being utilised, because we've now developed an underground GPS. GPS won't work underground. When we get the new city tunnel, you're not going to get a GPS signal. So we've had to use other types of navigation systems to assist our miners, making sure they cut straight, making sure they don't hit areas that are of danger. But more importantly, you can start removing the miner from the coalface. And before you say, if we do such, there'll be a job issue. When you remove people from a coalface, there's a lot of dust. So if you can remove people from a coalface, you improve their safety because they're not exposed to hazardous environments. You can improve the productivity, so everyone's happier overall. You can improve the job quality. And an independent report, we've had this operating now for 5 years in some trial mines, there have been no job losses. So the people have been redeployed to be used in other areas. And so where we utilise nanotechnology is more of a systems integration. How can we use these new technologies in mature industries to maintain our competitive advantage? I'll leave it there, Kate.
Thanks, Peter. And Peter.
Thanks, Kate. I've got a real fun job, actually. I get to play with nanotechnology and make the materials, make them into things. And as Professor Gray has said, 2 key areas are the areas of environment and energy. In the environment side, we're making new materials to clean the air, to clean the exhaust from cars and clean the pollution that could occur from industry. So cleaner air, less greenhouse gases, and that's one of the advantages of nanotechnology that we can bring. In the other area of energy, there's 2 sides to it. The first one is energy generation and then storage. In terms of energy generation, nanomaterials are having a big impact, and particularly in areas like solar technology. You can get nanomaterials now that you can convert into inks so that you can just print solar cells, run them off at a huge rate, cheaply, safely. So you now can produce solar cells that everyone can afford, so less than $1 a kilowatt. And this is now happening in around the world, and we're seeing gigawatts of power being generated this way. But the area that I actually have a bit of fun with myself is in energy storage. And here in Brisbane, we're making a material that's one of the new types of lithium batteries based on nanomaterials. Now, we've talked about nanomaterials, but I don't think anybody's sort of really said what they are. How do you make them? Are they safe? These are all the sort of questions everyone's going to ask. So I spoke to my children and said, what sort of questions would you ask? And they said, well, show us the kit, Dad, how do you make it? So I put one together. So this is my nanotechnology how-to kit. So you can come and get one of these and make your own nanotechnology. But the material that we make in the battery area is called lithium iron phosphate. It's a new type of lithium battery. So I've got the ingredients, lithium. So where does this come from? Is it a dangerous thing? Is it something we've got to be worried about? Well, actually, lithium's quite a high proportion of salt in salt water. And it's mined from salt lakes, and particularly Atacama Desert in Chile is one of the places where it's quite common. But it's common in seawater, so it's a salt. The next part of the battery is the iron. So in that particular case, we use iron oxide. Now, iron oxide is just another name for rust. So here's some that we ground up. So far we've got salt and rust in this battery. The last part's phosphate. And where do you get phosphate? It can be used in fertilisers, but the actual form that we use is the same as the one that's used in Coca-Cola. So the ingredients aren't too bad when you come to think of how you use them, but now you've got to put them together. You've got to have your nano machines, you've got to go and get the atoms of those and put them all together into the structure that you want for your new battery. So I've got my bottle of nano machines here. I won't let them out. They're quite safe. So what are the nano machines that we're actually using to create these batteries here in Brisbane? They're a bit scary for children, I must admit, because it's soap. Soap is all we use to put these things together. When you think of soap, there's different types. You wash your hair in one type, you wash your floor in another type, you wash your clothes in a different type. How many soaps would you come across in a single day? And so what we do is, the way that soap works to clean things is it has little charges on the surface. A soap molecule is only about 2 nanometers. So what we do is we put them together, we put these things into solution, into water, we put our soaps in, and they go and grab the atoms that we want, and we dry them out. So nothing too scary so far. And we just get a powdered material, something like this. So this is the new battery material that people are talking about around the world, lithium iron phosphate. So the thing about these new batteries being nano, they can charge extremely quickly, 10 seconds. They can hold a great amount of charge, so there's great opportunities here for storing solar energy, for use and applications. So you're probably used to this type of a battery in your computer. It's the old type of lithium battery, but the new ones you can make into much bigger forms. This is just a pack of the ones that I put together there. Now I'll just show you one other thing with these batteries, because we've had a brief look at how simply you can do nanotechnology. How do you use it? And we've sort of touched on that a little, but there's really practical uses of some of these things. This is a bit bigger battery, and it's the same material, the same sort of thing, but now it's a bit bigger than your computer. And if you give me just 2 seconds, I'll show you something you can use this one for. Nanotechnology is actually doing something to help the environment in just a simple, practical way. Now you can ride your push bike, and on those days where you don't really feel like it, you can still get away with it. So it's just an example of how, using nanotechnology, we've come up to this size of technology. It's the same technology that they're talking about in electric vehicles, hybrids, and fully electric vehicles that are now on the market. So this is the technology. Thanks, Kate.
And just to finish us off with our introductory session, I'd like to throw over to Dr. Nina Midder.
Well, after the 3 illustrious examples by the 3 big Peters, I feel a bit humbled. I have entered into the field of nanotechnology only last year, so I'm making my beginning in that area. And my area of interest refers to health. Well, this is something I think we all experience in our life, and if there are mums and dads in the crowd, they will relate to taking their child for vaccinations and for injections and a jab here and a jab there, and the mom feels the pain as well as the child feels the pain and the crying that happens. Vaccines, so my interest relates to vaccines. Vaccines, whether they are human vaccines or veterinary vaccines, they face some very critical issues. One of them, of course, being the big needle or the delivery of the vaccine. Other than the delivery or the needle-based delivery, the other factors which are critical to vaccine is that most of the vaccines that are used have to be stored at low temperatures or freeze-dried or stored in the refrigerator. It may not sound big, but for the developing world, it's a big issue to store the vaccines at low temperature. It adds to the cost of production, it adds to the cost of delivery. Having lived in India, I can really relate to it. When polio vaccine was available only as an injectable vaccine, it was so difficult to reach the masses with that vaccine. The moment a liquid oral dose of polio was developed, polio is almost now, we say that it's eradicated from India. So it's that kind of a big impact just by changing the mode of delivery of a vaccine that we can get and by changing how these vaccines need to be stored. Another issue that faces the vaccines other than that is multiple doses. Those vaccines that we use are not potent enough, and sometimes you have to go for one dose, and after 3 months there's a booster dose, and then after 1 year there's another dose. And this also once again impinges upon people's multiple doses. You can't reach for them or they're not available. And all these issues, I found we can find a way of addressing them by using nanoparticles. Now, nanoparticles, as people have explained here, nano is small. Small, very, very, very small. If you go from milli to micro, and to go even 1,000 times smaller, that is nano. So this is how, as he was showing, a nano powder or a nano vaccine may look like. Nanoparticles, because of their small size, have a very large surface area. So what we can do for creating a nano vaccine is that we take a protein from the disease-causing bug. The traditional vaccines either used a heat-killed bug itself or a weakened bug, which may have side effects. But for nano vaccines, what we can do is we can just take a protein from the bug and coat these nanoparticles with that protein. These nanoparticles will then, they are stable at room temperature, they can be stored at room temperature, and we can explore alternate routes of delivery. We can take them as a nano tablet, oral suspension, nasal spray, tattoos, patches. The list is endless, but these are all the possibilities that exist. With any kind of new technology, it's the testing of the new technology that is the critical phase, and that's what nanotechnology in the form of vaccines is going through. In my particular case, I'm working on a bovine viral diarrhea virus. It's a cattle virus. It's a huge problem for the Queensland livestock industries, with about 35 to 40% losses caused by this virus. And what attracted me to this virus, other than that we had the toolbox to work with it, was that if a calf becomes, a mother becomes infected with this virus, she gives birth to a calf who remains persistently infected with the virus throughout the lifespan. Not only that, that calf can pass the virus to other healthy animals within 1 hour. It can be through tears, saliva, vaginal discharge, semen, blood, sweat, anything, and that can be passed on. There is a vaccine available for it, but once again, it has to be stored at low temperatures, and 2 doses subcutaneous injections are required to the cattle at the right time. So with the help of Australian Institute of Bionanotechnology, I have a collaborative project where we are trying to develop silica nanoparticles, which is a chemically inert material, and our aim is to make a vaccine which would be, A, we would be able to store at room temperature, B, we would be able to explore some alternate routes of delivery, and 3, make it sufficiently potent enough that we do not require multiple doses. And like any, as I mentioned, new technology, and I'll be testing, although there are lots of relevant literature available in terms of the biodegradability of silica or non-cytotoxicity, but in our first mice trial, that is what we will again look for once we use these particles. Thank you.
Thank you.
I'm excited.
Well, that was a fantastic introduction to the potential for nanotechnology, and I'm personally incredibly inspired by some of the work that's being undertaken by these professionals. But I just want to take us back a step and just to talk a little bit about what we actually understand to be nanotechnology these days. And Peter Talbot, I was wondering if you could maybe expand on that a little bit, because obviously, as Nina explained, nano means very, very small, and I think the definition of nanometer is 1/1000th of a metre, so absolutely microscopically small. And some, probably because of popular media and fiction and other sorts of ideas that we've come across, we think of nanotechnology as very, very tiny machines. But clearly, from hearing all of the examples from the panellists this morning, it's not nearly that simple, and obviously the field is much broader than that. So could you maybe give us a little bit of overview about what we think about what nanotechnology is?
I suppose the first thing to consider is the scale. It's hard to grasp how small something like that is. And a good way is perhaps use an analogy and take something, first of all, the size that you know. An example might be, say a basketball. Okay, it's about this sort of size. Now, if you wanted to reduce its diameter down to, say, 4 or 5 nanometers, you'd have to reduce that diameter about 50 million times. Now, again, that's a bit hard to grasp, so I'll use an analogy of going the other direction. If you reduce the size of the Earth in its diameter 50 million times, you'd end up the size of the basketball. So it's a huge difference in scale. Nano is only 1 order of magnitude above an atomic scale. So firstly, that's the first main thing. Try and understand the size. The second thing is the level of development that we've reached at this point. And as you say, there's some interesting books. I think Michael Crichton did the Grey Ooze book, where they all got away and everybody was converted.
I'll come back to the grey goo in a minute.
But nanotechnology can go from very simple things to the very complex. But at this stage, the nanomachines that you're talking about are only in the concept stage. I've seen some development of that work. That's not to say that nanomaterials themselves, just from their size, aren't extremely useful, and I think you've heard that from people here.
So we're really talking about everything from basic materials, particles, as Nina was talking about, and what we can coat them with and how we can use those, but also to cells, to machines potentially if it develops beyond the concept stage.
Stanford in the States have been able to produce walking DNA, so it's up to that level of development. So it is quite, from the quite simple to the quite complex.
Maybe something that Nina and Peter Gray could comment on. When we talk about the area of health, understandably, I think that when we're talking about a technology that many of us find difficult to conceptualise or understand, we feel an element of trepidation about what the unforeseen outcomes might be of experimenting with this kind of technology. Have you encountered any of that through your work?
Just to start with, maybe I'll comment on that. It's just using a small size particle to deliver something, and you're right, it's the question, whenever you change something which relates to human being or human health and actual intake, it does raises questions, whether it's going to be safe, how is it going to be, and I think the nano people are very well aware of it. Especially in the area of biology, whatever research is being done, they're taking care that their starting material is actually a biocompatible material, a material which is already Like, for example, I talked about silica. Now, silicic acid is something which is present everywhere in plant. Like, I'm a plant biotechnologist as well, and my other project relates to how silicic acid application to the roots of a plant makes it more resistant to fusarium wilt or a disease of banana or a disease of chickpeas. So these are the kind of materials which the nano people are actually exploring to load the vaccine onto. So these kind of safety issues are big issues, and they are being addressed not only from the toxicity angle but also from the degradability angle as well. Like, how long will this silica remain in the system, whether it will be excreted out or whether it will just degrade. And all these answers are being found very, very positively. Then only the next step is taking place. So it's not as if, you found a material, you load your protein, and yes, it gives you a protection against the disease and you move on. There are all these very critical aspects, especially in relation to drug and vaccine delivery, which are being looked into.
Peter Gray?
Yeah, I agree with those comments. I mean, the first nanoparticle approved for human health a few years ago actually packages a very insoluble compound, paclitaxel. It's very toxic and used in chemotherapy, treating cancer, inside a nanoparticle of human serum albumin, which is a protein that's in all our blood. So that went through the testing, which is very extensive in any human medication, to prove it was safe. Why it was effective as a product was that the body saw this particle of its own protein in effect, would then take it up in cells that were tumour cells, and then the release of the toxic agent could kill those cells. And the next generation nanoparticles is where you might label the particle by putting on, say, an antibody fragment that will only recognise tumour cells. So these particles could then float around the body. You might have removed most of the tumour by surgery or other major technique, but these particles could target out the remaining tumour cells that are expressing what's called a marker, or something on their surface that indicates them as different, and then the particle goes for those cells and destroys the residual tumour cells. So these generations of development is what the research going on in Brisbane and globally is trying to develop.
Could I add something?
Please.
Just on this drug that Peter just spoke about, what motivated people was that this drug, Taxol, is a great breast cancer anti-agent. And for a female subject to go through the preparation of taking this raw drug, it was very painful. There was a lot of pre-treatments required, a lot of steroidic treatments required, because the solvent that the drug had to be dissolved in was actually, pretty toxic itself. So the motivation was, how can we deliver this very useful compound to someone who really needs it today, and how do we make sure that it gets to them in the right amount in the right time? So the motivation was done through human health and a desire to make sure that this particular drug got to where it had to get to with giving the least possible inconvenience to the patient.